Using our next example, here's the factors of 10. 1 times 10, 2 times 5, over the factors of the leading coefficient, 1 times 4 or 2 times 2. So now we start writing out all of the potential ones. So we'd have 1 divided by 1, 1 divided by 4, 1 divided by 2, 10 divided by 1, 10 divided by 4, 10 divided by 2, 2 divided by 1, 2 divided by 4, which is a half, we already listed that one, and 2 divided by 2, which is 1, we already listed that one. 5 divided by 1, which is 5, we got it. 5 divided by 4, and 5 divided by 2, we already got that one. So these are all the potential zeros. Now, why are the potential zeros worth finding? Because when we take the potential zeros, these are the only numbers we have to try to see if it is a factor. So if we plug in a 1 and this ends up giving us a 0, then we would know that x minus 1 would be a factor. If we tried 5 halves in for the x and it gave us a 0, we would then know that x minus 5 halves would be a factor. So now you know that these are the only ones you have to try. These are all your potential zeros. All right, another theorem is when we have complex roots, there's always the conjugate pair, meaning if you have x plus 3i, then there should be x minus 3i. If you have 2 plus 5i, then you should have 2 minus 5i. There's always conjugate pairs. Same could be said for the roots with the square roots. Anytime you square root, you always have plus or minus. So if you have 2 plus root 5, then you have 2 minus root 5 is also a root. So make sure that anytime you see an I, which means the square root of -1, right? Anytime you see an I, it means you have a square root, and anytime you have a square root for one of the roots or zeros, then you also have the negative version of that. So a polynomial function with rational coefficients has the given zeros. We want to list the additional zeros the polynomial must have. So if we have this problem here, we have 2 plus root 7, we have -9, and we have 3i. What are the other zeros that this polynomial must have? So according to this root 7 here, we should also have a 2 minus the square root of 7. And because of this 3i, we should also have a -3i. So these are the ones that it must have. It must have 2 minus root 7 and also -3i. So if the roots or zeros are 5, 0, -7, and the square root of 3, then the only other one that must be there is the negative square root of 3. And here's your last example for this. If you have 7 minus I, 5 plus 3 root 2, and -11, there are two other roots that must be there. 7 plus I, and 5 minus 3 root 2. These are the other roots that must be there. And now we're going to learn something called Descartes' rule of signs. This helps us determine how many positive zeros there are, how many negative zeros there are. And these are dealing with real roots, not imaginary roots. So for the positive, we want to count the number of sign changes that the function has. And for negative, we want to count the number of sign changes that the function has if we were to plug in negative x. Now, these are always going to be in pairs. Or in other words, we always go down by 2 for possible number of solutions. So for example, if we came out with 6 sign changes, then there could be 6, 4, 2, or 0 positive ones. If we came out with the number 5, there could be 5, 3, or 1 real positive solutions or roots. So just remember that it always goes down by pairs. All right, so using Descartes' rule of signs, we're going to name the possible number of positive and negative zeros. So for positive zeros, remember we take the function, we count how many sign changes. So this positive, negative, positive, negative, positive, right? So we change from positive to negative, that's 1. From negative to positive, that's 2. Stayed positive. Then positive to negative, that's 3. And negative to positive, that's 4. There were 4 sign changes. So that means that there are 4, 2, or 0 positive zeros. Positive real zeros. Okay, then we're going to go back to this function, and we're going to plug in a negative x for all of the x's. Right, so now that we've plugged in the negative x for all the x's and we've simplified our function, we can see that these are all negative and then these are all positive. So it went from negative to positive. That is 1 sign change, which means there is 1 negative real solution or real zero. All right, so here's another problem. We have to find the positive and negative number of real zeros using Descartes' rule of signs. So we started out positive, negative, positive, negative, positive. So it changed 1, 2, 3, 4 times. So again, we have 4, 2, or 0 positive real solutions or real zeros. If we plug in a negative x for all of these, this would stay positive. This one would go to positive. This one would stay positive. This one would go positive. And this one would stay positive. So there are 0 changes. So there are 0 negative real zeros. Now you have all the information you need. Please work on your assignment.